All right, so today we are going to look at section 5.4 related rates. So for this section, we are going to look at the relationship between some variables. And then, when you take derivative, you're going to get the rate of change. Uh, in this section, the problem will be like you are given some situation, and then they're gonna ask you to solve for something. So what you have to do is here, look at the summary in the box. So you have to read the problem carefully. Next, you need to draw a diagram if possible, and then after that you need to introduce the notation. Well, the idea is you try to assign the symbols to all quantities that are given in the question, and then after that you're trying to express the relationship between them. Well, once you express the relationship between them, so you can take the derivative with respect to t. So when you differentiate with respect to t, sometimes you need to use the chain rule. And then after that, you substitute the given information to solve the quantity that you want to solve for. Well, here this is a theory, but this is the steps that we should do when you uh, face the problem of related rates. Well, I'm gonna show you 3 examples, and hopefully you absorb the technique from those examples. All right, let's start looking at example 119. So all of these questions in this section gonna come in word problems. So what you need to do is you need to read first and trying to translate everything into mathematical terms. So example 119, a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at the rate 1 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So if this is not given in the picture, so you should be able to draw it by yourself. But this is very first example, so I'm gonna draw a picture for you. So let's say that you have a ladder here that I draw in red. So you know that the ladder is 10 feet long. Well, you have the wall here. This is the wall, the one that I draw in green. And the ground here gonna be the one that I draw in uh, blue. So for sure, you can let x be x and y. So I will let x and y be distances defined in the picture. In the 1 second, in the picture. So you can see that in the picture, well, we're gonna let x to be the distance from the corner here that I trying to do a dot here from the corner here to the bottom of the ladder. This is going to be my x. So my y value gonna be from the corner here to the top of the ladder. This is going to be my y. So I have x and y here. So if you look at the question asks you how fast is the top of the ladder sliding down when the bottom of the ladder is 6 feet away from the wall. So actually they ask you for dy by dt. So they want to know what is the rate of the change from the, of the distance that you measure from the top of the ladder. Well, that is dy by dt. They ask for dy by dt when the bottom of the ladder is 6 feet away from the wall. So when x equal to 6, this is what you want to solve for. You want to solve for dy by dt when x equal to 6. Well, once you have everything ready here, so you can see that what you need is you need the relationship between two variable x and y, right? You have x and y here, but you need the relationship between them. So for sure, when you see a right triangle here, everyone should know that when you see a right triangle here, what can help you is Pythagorean theorem, right? This thing gonna tell you that, hey, if you have a right triangle, so then you have x squared plus y squared equal to, well, 10 squared, right? This is by Pythagorean theorem. So I'm gonna use this as a base to solve this question. So I'm gonna say that by Pythagorean theorem. So we have x squared plus y squared equal to 10 squared, which is 100. So this is going to be our relationship between two variables. So if you want to find dy by dt, yeah, for sure, we need to differentiate this thing. So we're going to differentiate that, well, by using the implicit differentiation technique. So I have to x dx by dt, right? And then plus 2y dy by dt. And then differentiate 100, I get 0. So from this step to this step, I differentiate with respect to t. Okay. Sounds good. Next, we are going to plug in our numbers here. So we know that what we want is dy by dt, right? So we want dy by dt when x equal to 6. So we can plug in x equal to 6. We can plug in the x by dt equal to some number. So what is going to be the number of the x by dt? So the question say that the bottom of the ladders lie away from the wall at the rate 1 feet per second. So that means it is given that the x by dt is 1. I'm going to use the black color, so they are the same. All right, plus 2 times y. What is my y now? So you can see that when x equal to 6, you can find y, right? Because when x equal to 6, you know that 6 squared plus y squared going to be 100. So that means y is 8. So you can solve for y. So that means y squared is 64 and y must be positive because this is the length. So that means y equal to 8. And the quantity that we want is dy by dt, given that x equal to 6. This is the one we want. So you can simplify a little bit more and then, you know, move something and then subtract something. So you're going to have 16 times dy by dt, where x equal to 6. This is going to be negative 12. Well, that's mean dy by dt, where x equal to 6. This is negative 12 over 16. Well, make it cleaner is negative 3 over 4. The unit is going to be feet per second. All right, so this is your answer. So the answer is going to be negative 3 over 4 feet per second. Well, you can see that this is negative because this represents how fast is the top of the ladder sliding down. So because it's sliding down here, so it's going to be negative dy by dt. The quantity here is going to be negative. Does it make sense? So this is our first example of related rates. And I hope you see the big picture now. The big picture is after you read the question, you're going to translate it into mathematics. I mean, in terms of x, y variable, and then you can differentiate with respect to t, and then solve for the interested quantity. That is all for this section. Supposed to be super easy if you understand the problem. I mean, if you can translate this into mathematical form, well, the rest is going to be easy. All right, so we have two more examples. So example 120. So let's do something related to a sphere. So air is being pumped into a spherical balloon so that its volume increased at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when diameter is 50 centimeters? So here we have a sphere. Well, we can imagine that the balloon is a sphere. And then for the sphere, they're going to have a radius r, right? Well, the thing that you need to know is the volume of the sphere, right? So the volume of the sphere, so if you remember the formula from high school or something, the volume of the sphere going to be 4 over 3 pi r cube. This is the volume of the sphere. If you don't know it before, memorize. This is the first time. If this is your first time you see it, memorize this thing, because this is the formula of the sphere, the volume of the sphere. And then, well, we can let this thing to be V, the volume of the sphere. You can see that the question gives you that the volume increase at the rate 100. So it is given that dV by dt equal to 100 centimeters cube over per second, right? This is given. So what you need is you need how fast is the radius of the balloon increasing when the diameter is 50. So actually you need dr by dt, right? This is what you need. So you need how fast is the radius change when diameter is 50. So that means when r is equal to 25. Does it make sense? Because diameter is 50, so radius is 25. So this is what you want. And you can see this question is super easy because you have v equal to 4 over 3 pi r square or pi r cube, sorry, already. So you just need to differentiate that with respect to t. So differentiate with respect to time t. So you're gonna have dv by dt, and this is 4 over 3 pi. So this is constant, so I pull out. So I only need to differentiate r cube. So I have 3r squared dr by dt. Oh, this is by the chain rule. And then after that, so I plug in dv is equal to 100. And then 4 over 3 pi. Well, I'm gonna cancel 3 first because I don't like that. So I have 4 pi r squared. So what is r squared? R is equal to 25, right? Because I want to compute dr by dt where r equal to 25. Wow, that is pretty simple. And then dr by dt where r equal to 25, this is going to be 100 over 4 pi times 25 square. Cancel a little bit, so you're gonna get 1 over 25 pi centimeter per second. All right, this is my answer, our answer. Well, pretty simple, right? You see, if you figure out the relationship between two quantities and then you differentiate with respect to t, that's all for this section. And there's going to be one question on the exam about related rates. Well, you shouldn't miss this question. This is the simple one. On homework for question 3, that is a question on related rates too. Well, the homework this week on Saturday that you have to submit, you're going to see one question on related rates. All right, so the last question on related rate, the last example for this question, I'm going to show you how to do this problem because we need the idea of similar triangle on this question. All right, example 121. A water tank has the shape of an inverted cone, a base, radius 2 meter, the height is 4. So we have a picture here. So you know that the height is 4 and the radius is 2. If water being pumped into the tank at a rate 2 cubic meters per minute. So the water gonna come up, I mean, just get into the tank with a rate 2 cubic meter per minute. Well, we want to find the rate at which the water level is rising when the water is 3 meter deep. So this question is a little bit complicated in terms of you have more than two variables at the same time, right? Simultaneously, you have H. This is going to be the height of the water at the time t. You have R. This is going to be the radius uh, of the water level at the time t. And then you also have V, which is going to be the volume of the cone. Well, I can say VT, this is the volume of the cone at the time t. So the volume of the cone, well, you need the formula of the volume of the cone anyway. So the volume of the cone is going to be V equal to 1/3 times pi r square h. If you don't know this thing, memorize. This is the volume of the cone. Well, if you can memorize the volume of the cylinder, so the volume of the cone is going to be 1/3 of the volume of the cylinder. And then after that, well, the volume of the cone here going to give you a relationship between V, R, and H, right? However, uh, this is related rates problem. You need only two variables. So you need to get rid of one variable, R or H. Well, otherwise you're going to have too many variables and then you cannot do the related rates problems. So let's look at the question again. The question asks you, well, I'm going to highlight this thing in green. So the question asks you the rate at which water level is rising when the water is 3 meter deep. Well, we're going to save our H because we want to find the H by dt, right? Because the question asks you the rate at which water level. So water level is rising. This is going to be my, well, the question asks you for the variable H. So we're going to save our H here. That means we want to find the H by dt where H equal to 3. So that is what we want. But what is given is we know that the water is pumped into the tank at the rate 2 cubic meters per minute. So what is given here? This is dV by dt equal to 2 cubic centimeters per minute. Well, that means you have dV by dt. You want the H by dt. So from the given relationship here, you should get rid of R and then, swap it into H somehow. So how could we do that? So if you look at the picture, you can see that we have a right triangle here, right? And then the cone has radius 2 and the height 4. However, at the water level here, you're gonna have the height h and radius r. So if you use the similar triangle, which means the ratio from the small triangle here must be the same ratio with the big triangle here. They must have the same ratio. So which means the similar triangle gonna give you uh, 4 over h equal to 2 over r. Does it make sense? This is going to be from the similar triangle because the big triangle gonna have the height 4. The small triangle gonna have the height h. The big triangle gonna have the radius 2. The small triangle gonna have the radius r. So it must be a proper ratio. So that means you also know that h is equal to 2r, or r is equal to h over 2. All right, r equal to h over 2. We have that. So the relationship between r and h, it does come from similar triangles. And then now you can plug in this thing back into the relationship. So I'm going to get v equal to 1/3 times pi times Well, this is h over 2 square times h. Well, this is 1/3 times pi times h cubed over 4. Well, simplify a little bit more. So pi over 12 times h cubed. So now the relationship just reduced to v equal to pi over 12 times h cubed. So now once you have v equal to pi over 12 times h cubed, so you can differentiate with respect to t. So you get dv by dt equal to pi over 12 and then 3h squared dh by dt, right? This is by the chain rule again. And then now you are ready to plug in everything. So you can plug in dv by dt to be 2. You can plug in h to be 3. And then what you need is the h by dt at h equal to 3. Right? You plug in everything you want. Well, the h by dt at h equal to 3. This is, well, let me compute this thing. 24 over 3 times 3 times 3 is 27 pi. All right, this is 8 over 9 pi. Well, the unit going to be the unit of h, which is going to be meter per minute. Oh, 1 second. Yeah, meter per minute. So this is not centimeters, sorry. dv by dt, this is not centimeter. This is just cubic meter. All right, I wrote it wrong. Okay, so the answer going to be 8 over 9 pi meter per minute. Well, not hard at all. This is for the related rates. So any questions in the chat, please, for related rates. So we're going to move to the next section, indeterminate form, which is the last one for this chapter. Well, of course, you have a practice at home. Example 122, 123, and 124. Those are examples for this section. So I already did the solution on this thing. Well, I'm ready to post it after class. But you know what? You're gonna learn when you do the problem by your own. So please do that before you look at my solution. Because if you look at the solution right away, well, you didn't practice anything. And then on the exam, you're gonna have the same problem that, hey, I don't know where to start. So try first, and then you just check with my solution online. So that's the best way to learn. You know what I mean? Because I mean, some of you just watch my clip again and again, but you have, I mean, you didn't practice at all. You just listen to me. Because when you look at me doing problems, well, it look easy because, you know, I did this thing so many times already. But for you, it may be, you know, take some time that to just start the problems. All right, so I'm gonna post the solution here after class for sure on the clip, but well, let's skip that for you to practice on those 3 examples. So we're gonna look at the last section for today and the last section for this chapter, indeterminate form. All right, sounds good, everyone. We have, well, today we have only 29 students, so getting smaller class. Well, let's check in. So I want to know who is in today. So for those of you who are in today, let's type something in the chat so I know that you are in today. So, well, I can help people who attend the class then. Okay, something good. I know you are tired from physics class, but well, I don't know. Anyway, but well, stay with me for 1 more hour. So we're gonna finish this section 5.5. This is the easy one though, man. Everyone, this is the indeterminate form. So for those of you who know this thing already, this is going to be super easy. So in this section, the main thing we are going to learn indeterminate form, which is going to help us to compute limit. On the midterm exam, so well, 1 second, I check the chat now. So everyone type, okay, good. So On the midterm exam, some of you did use the L'Hopital rule, which I gave you. Like, I mean, if you use the L'Hopital rule on the midterm exam, out of 3 points, I give you 0.5 because, well, I haven't taught that thing at that time. But well, now it's the time to learn the L'Hopital rule. So let's look at that thing together. So you can see that in chapter 1, you have something in the form limit of fx over gx, man. And I told you that when you have 0 over 0, before midterm, I told you that you have factoring, conjugate, maybe use the trigonometric limits, maybe you use the squeezing theorem. So you have few choice to solve limit f over g. However, sometimes factoring does not work. Sometimes conjugate does not work. You can use something called the L'Hopital rule. Well, this is the statement of the L'Hopital rule. Well, the L'Hopital rule says that if you face the limit fx over gx, and you know that limit of fx approach 0 and limit of gx approach 0, then you can differentiate the numerator, and then you can differentiate the denominator, and then you compute limit. Wow, this is amazing, because that means if you see the form 0 over 0, which we are going to call it indeterminate form, we're going to use the notation if 0 over 0. This is going to be the notation for indeterminate form 0 over 0. Then you can apply the L'Hopital rule. So that means you can differentiate the numerator and differentiate the denominator and then compute limit, which usually good because you reduce, well, by differentiation, you reduce the complexity of the function into something, something clean, something that is, less messy, and then you can just find limit easily. Another form that you can use the L'Hopital rule is going to be the one that you see the limit of the numerator is going to be plus or minus infinity, and limit of the denominator going to be plus or minus infinity. If you see indeterminate form infinity over infinity, you still can use L'Hopital rule. This is only 2 forms that you can use L'Hopital rule. So the proof of this thing, well, I'm not going to say it here because we don't have time. But for those of you who want to talk about the proof of the L'Hopital rule, so, well, you can get in touch with me by email. Well, we can look at the proof of the L'Hopital rule together. But usually for math students, they're going to learn the proof of the L'Hopital rule on the 3rd year in the real analysis subject. But for here, we're going to just skip the proof and just use the result first. Well, again, if you want to see the proof of this thing, which is not that hard, well, but it takes some concept of real analysis. But, well, if you want to talk about the proof, well, chat with me privately after class maybe. So, well, I'm going to show you how to do this thing first. So if you have the example like this that I draw the arrow line here, so you can differentiate it. Before you differentiate, everyone listen to me, before you differentiate, check first if you have 0 over 0 or infinity over infinity or not. So I'm going to plug in that thing. So I'm going to plug in number 2 into the function. So I have 2 square minus 4 over 2 square minus 3 times 2 plus 2. Well, if I compute this thing, then I get 0 over 0, right? That means I can use the L'Hopital rule. Well, once I know I can use the L'Hopital rule, well, I'm going to make sure that this is indeterminate from 0 over 0. So I'm going to differentiate the top, which I get 2x, differentiate the bottom, so I get 2x minus 3. And then now I can plug in number 2, which is going to be 4 over 1. Is that right? 4 minus 3, 1. Yeah, the answer is 4. Simple, you see. You don't have to factor, or you don't have to do conjugate or something. You can use the L'Hopital rule now. Super easy. So the next one, x go to infinity of this thing. So you can see this is the indeterminate form, infinity over infinity. Because if you plug in infinity there, so you're gonna get two big number as a ratio. So here you're gonna you're gonna differentiate the top, which is 1, differentiate the bottom, you get 2. Dang, this is 1/2. Why is it so easy like that? You know. Woo. All right, next we are going to look at a quick review here. Well, some of you have a hard time to compute limit. So I'm gonna, let's recall some function that you may have seen. So you're gonna have, well, again, this review, make sure you know how to compute this thing. Some of you are gonna have a hard time when you see logarithm of x because you don't know what is the limit of log x. So keep in mind that when you have the graph yx here, the graph y equal to log x is like that. And then when you compute limit, when x go to plus infinity, so you're gonna get plus infinity. And then when you take limit, when x go to 0 from the right, you're gonna get negative infinity. Well, this is the one that students usually make a mistake. And also the one is arctan. This is the one that students don't know when we ask the limit of arctan. Well, the graph of the arctan gonna be something like that. Well, which means the limit when x go to plus infinity is pi over 2. And limit when x go to negative infinity is negative pi over 2. This is the one that we asked you a lot on the previous exam and, well, from the previous year. But usually students stuck on this thing because they don't know the pattern of log and arctan. So I just recall it for you here because for sure you're gonna use this thing again and again and again and again. All right, so for note 1 and note 2, you can read it by yourself. There's nothing much. I just show you how to do L'Hopital rule. All right, let's do real example. So today we're gonna have few examples to show you and also the practice at the end for you to practice. All right, so let's start from looking at example 125. So the first one is going to be the one that I asked you for limit of log 3x plus 5 over log 7x plus 3 plus 1. All right. Any question in the chat? Let's see first. No, okay, everyone good? All right. So as I told you before you do this problem, you should state that this is a problem about indeterminate form. So I'm going to plug in uh, infinity first. You can see that, hey, if I plug in infinity here, so 3x plus 5 going to be infinity. Log infinity is infinity. So on the top, I have infinity. On the bottom, I have log infinity again, plus 1, which is still infinity. So actually, this is indeterminate form, infinity over infinity, which means you can use the L'Hopital rule. So you're going to apply the L'Hopital rule here. All right, which is going to be limit x go to infinity. All right, so let's differentiate log. So differentiate log 3x plus 5. So I get 1 over 3x plus 5. By the chain rule, I need 3 here, right? Can you follow me? Yep. Then next, 1 over 7 plus 7x plus 3 times 7 here. Wow, that's from L'Hopital rule again. Well, differentiate 1, you get 0. Fine. And then now you can simplify a little bit. So that will give you 3 times 7x plus 3 over 7 times 3x plus 5. And here we get 1 as the answer. Can you follow me? Well, if you are fast enough, you can say this is 1. Well, if you don't, well, because I see that this is a ratio of polynomials, right? When you have the ratio of polynomial, you can, and you have the highest degree is equal to 1 on both numerator and denominator. So the ratio of the leading coefficient going to be your answer. If you feel like, hey, Ajahn, this is too fast, you want to go slower, so you can do limit 21x plus 9 over 21x plus 35. And then you can see that this is going to be 21 over 21, which is going to be 1. Something like that. All right, next, we're going to look at limit of this function where x go to 2 pi. Well, I told you this section is super easy. You should be able to do this question, this section, because, well, compared to the thing that you're going to learn next week, the integration, this is a lot easier. All right, here we are going to plug in 2 pi here, so you get 2 pi, oh man, sine 2 pi plus 2 pi square, and then minus 4 pi square. All right, 2 pi minus 2 pi. Yeah, for sure, this is 0 on the bottom, and on the top, this thing cancel, right? And then sine 2 pi 0. So again, they're all 0. So, well, this is actually indeterminate form, 0 over 0. So once you know that this is indeterminate form, 0 over 0, you can apply the L'Hopital rule. So to apply the L'Hopital rule, I'm going to say that I differentiate. Well, let's do the denominator first. Differentiate x, you get 1. Differentiate 2 pi, you get 0. On the top, I differentiate x sine x, so I get x cosine x, and then plus sine x. Well, this is by the product rule. I differentiate that, I get that, right? By the product rule, right? Well, I'm gonna delete that thing because it looks messy to me. Okay. Next, we are going to differentiate x squared, so you get 2x. Differentiate 4x, so 4 pi squared, that is constant, so I get 0. All right, you can see that, well, L'Hopital rule help us because it looks cleaner now. So I have limit x go to 2 pi x cosine x plus sine x plus 2x. All right, and then plug in. So that is 2 pi times cosine 2 pi, which is 1. Cosine 2 pi is 1, right? Yeah, cosine 2 pi is 1. And then plus sine 2 pi, which is 0. All right, and then plus 2 times 2 pi. All right, at the end we have 6 pi. This is your answer, right? Is it easy, right? All right, any questions so far? Well, all right, we have one more example before we look at another form of indeterminate form. All right, hopefully we can finish in 40 minutes, people. All right, example 126. Well, this is going to be more complicated one for the indeterminate form, infinity over infinity. So let's first you see that if x go to plus infinity, if you plug in e to the infinity, going to be infinity, right? And then you have e to the infinity, going to be infinity as well. You add them up, so the top going to be infinity. Well, the bottom here going to be infinity as well. Clearly, this is infinity over infinity. Well, you have to apply the L'Hopital rule. Well, before you apply the L'Hopital rule, well, you can see that you can make it better because here you have log e to the x squared. You can move x squared down. So you can cancel something first. So what I'm going to do is I'm going to copy the question first. Well, but the term that I highlight in yellow, here you can see that I can simplify it to x squared log e, right? You agree with me? You agree with me? Because I move x squared down, right? I can move this thing down because the property of logarithm. And then after that, I can, well, log e is 1. So this is 1. So it's go away. I have limit x go to plus infinity. So I can cancel x one time. So I have e to the 2x plus x over x e to the x. So this is a lot better in terms of you pull out one x and then you cancel. So if you cannot follow me, I pull x out one time and then I cancel it. And then after that, well, I'm trying to make my function a lot easier to differentiate, right? Because I don't want to differentiate the whole thing, which is going to be, you know, the messy term. So I'm going to differentiate that. Now I can apply the, well, this is still indeterminate form, infinity over infinity, right? So we're going to apply the L'Hopital rule here. So once you apply the L'Hopital rule here, so you're going to get, well, differentiate e to the 2x, 2e to the 2x, plus differentiate x, you get 1. Differentiate x e to the x, well, no ways you can do that easily. You have to use the product rule. It's going to be x e to the x plus e to the x. This is by the product rule, right? Just u dv plus v du. And then after that, hey, let's check if this is still indeterminate form. Well, is this an indeterminate form again? Well, it's still, right? It's still indeterminate form, infinity over infinity. Well, would you prefer to differentiate more? Well, you can see that if you differentiate more, the thing is that you're going to get something that is bigger, because your x e to the x here, you're going to still have the product of x and e to the x. It's going to give you more problems because you're going to get e to the x always. Just keep going, keep getting bigger. So the idea is, why don't we just simplify? So sometimes you need to simplify first to make sure that you can cancel something and the term is getting smaller. So here I'm gonna, well, what I'm gonna do is I'm gonna pull out e to the x. So e to the x here, I'm gonna pull out because this is my problem. Well, on the top, I'm gonna pull out e to the x too. Well, if I pull out e to the x, so here I get 2e to the x, right? Well, but how can I pull out e to the x from 1? Well, I get e to the minus x here, and then I can cancel that. Well, the reason why I do this, because once I have this thing, well, this is still indeterminate form, infinity over infinity. However, it looks much better because in the denominator, I have x plus 1. Well, once you differentiate x plus 1, it's going to go away. And then we're going to have the answer we want, right? So we're going to say that this is going to be our limit x go to plus infinity. We differentiate one more time. This is the step that we use the L'Hopital rule again. Well, this question is not easy, man. This is the hard one. Differentiate 2e to the x, you get 2e to the x. Differentiate e to the negative x, you get negative e to the negative x. Differentiate x, you get 1. Differentiate 1, you get 0. Well, at the end, you get limit x go to plus infinity 2e to the x minus 1 over e to the x. Well, which you can see now that if you plug in infinity, hey, you're going to get infinity minus 0. Well, which is infinity? So the answer is going to be plus infinity. So this is the hard question. Well, should be the A-level question, I think. Well, some of you are going to say, oh, John, this is not that hard. Well, but, well, this is hard enough to cut B plus and A level for the class. All right. That is the idea of indeterminate form. Well, to sum up, well, I'm going to write it here. To sum up, if you see 0 over 0 or infinity over infinity, you can apply the L'Hopital rule. And that is going to be your friend because you can, once you apply the L'Hopital rule, everything going to be smaller and nicer, and then you can compute limit easily. All right, so we have 2 more topics for today. And, well, 2 or 3, I cannot remember. But anyway, well, few more examples, and then we're done with chapter 5. All right, be patient, everyone. So the next one is indeterminate products. So you can read this thing by yourself, but I'm gonna sum it up for you. So the idea is you could have the indeterminate form 0 times infinity. Sometimes when you plug in, you could have 0 times infinity. This is going to be the one that, well, 0 times infinity, this is not 0, and this is not infinity. We do not know which one is, uh, which one is a winner. We do not know. So because from here we already know that one term it approach 0, one term it approach infinity. We This is called indeterminate form. So the way to solve this thing is you're gonna simplify it. You need to simplify it into indeterminate form 0 over 0 or indeterminate form infinity over infinity. Well, and then you can apply the L'Hopital rule after. That is only keyword here. So if you see example 127 here, well, you can see if you plug in infinity, so you have infinity times log 1 plus 1 over infinity. This is infinity times log 1, which is infinity times 0. Hey, Ajahn, this is infinity indeterminate form 0 times infinity. Well, you cannot answer anything right now because this is one form of indeterminate thing. You just need to simplify first. What I'm going to do, I'm going to simplify it to 0 over 0 or infinity over infinity. You can see that if you move x down to 1 over x, here, now you're going to come back to indeterminate form 0 over 0, right? Because on the top, you're going to have log 1. On the bottom, you're going to have 1 over infinity, which is 0 over 0 now. All right. And then after that, well, once you have 0 over 0 now, all right, our friend L'Hopital rule. All right, we apply the L'Hopital rule, so we're going to take derivative. So on the top, you're going to have, well, let's go slow, 1 over 1 plus 1 over x, right? And then differentiate that, you get 0. Differentiate 1, you get 0 by the chain rule. Differentiate 1 over x, you get negative 1 minus 1 over x squared. And then differentiate 1 over x, negative 1 over x squared. All right, if you feel like, hey, Ajahn, I need more time to differentiate 1 over x, that's fine. Take your time. But, well, I know how to differentiate 1 over x quick, so I just differentiate 1 over x, so I get negative 1 over x squared. So now it's time to simplify it. So you can see that this thing that I circle gonna go to negative 1 over x squared, which is going to be the same thing with this term. So I can cancel out. So I'm gonna have limit x go to plus infinity of 1 over 1 plus 1 over x. Well, this is 1 over 1, which is 1. Right, 1 over 1 plus 0 actually, which is 1. Wow, easy, right? All right, next. Any questions so far? Well, I told you can stop me in the chat now. Because let me see. Well, here I'm gonna show you in the clip, I think, because we ran out of time. So let's watch the clip later because, oh, let's see. We still have 1, 2, 3, 4, 5, 6, 7 pages left. So I'm gonna show you in my video clip. So let's watch this thing on my channel. Watch solution on my channel because we don't have time now, people. Well, we don't have a makeup for my class, but well, in order to do a makeup, so you just watch my channel. So the idea here is when you plug in infinity, people, you're gonna have infinity plus 1 square pi minus 2 arctan infinity, right? Well, an arctan infinity gonna go to pi over 2. So actually this is pi minus 2 times pi over 4 or pi over 2, and then this is infinity square. Well, it's actually indeterminate form, 0 times infinity. Well, actually, if you try to plug in infinity, this is indeterminate form, 0 times infinity. And we can solve this thing by just swap it to 0 over 0 or infinity over infinity. Well, if you want to try it at home, try it and check the solution online on my channel. All right, so we're going to move to another form, which is, so we already learned 3 forms, which is 0 over 0, infinity over infinity, and 0 times infinity. The 4th one going to be infinity minus infinity. The keyword of this one is when you have infinity minus infinity, you don't know which one is bigger, right? The first infinity could be very, 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 strong compared to the second one. Well, it could end up with 0. Any number or plus or minus infinity can be anything. So this is another indeterminate form. We're going to say this is indeterminate form, infinity minus infinity. Well, the way to solve this thing is, unfortunately, you have to simplify it. The only way to do it is simplifying. No choice. You just need to simplify it. Well, let's look at example 129 here. Let's say I have limit of secant x minus tan x. How do I do this thing? So I'm going to simplify it by, well, first of all, if I plug in, this is x go to pi over 2. If I plug in x equal to pi over 2, secant pi over 2 is infinity. Tangent pi over 2 is infinity. So infinity minus infinity, right? So this is actually the indeterminate form. So what you can do is you can simplify it, though I swap secant to 1 over cosine, tangent to sine over cosine, and then you find the common denominator, and then you're going to see that, hey, at the end you have 1 minus sine x over cosine x here, and then you can apply the L'Hopital rule, which is you're going to get 0 at the end. Sounds good. So I'm going to show you example on this topic so you know how to do it. All right, example 130. Let's do this one together. So we have limit of cotan x minus 1 over x. So we need you to use the technique that, well, you can see that cot 0, this is infinity. And then 1 over x, this is, if you plug in 0, this is infinity. So this is actually indeterminate form, infinity minus infinity. People. All right, that is good. So, well, we're gonna simplify first. Let's do it. Cotan x minus 1 over x. So this is going to be cosine x over sine x minus 1 over x. Well, if you find the common ratio, this is going to be x cosine x minus sine x. Well, this is your function after you simplify it. And then now you take limit x go to 0. Well, start from the cot x minus 1 over x, right? You simplify it. So you're going to get x cosine x minus sine x over x sine x. Well, once you simplify it, you can see that now it's come back to indeterminate form, 0 over 0, right? Because you have x here, which is going to give you 0 on the denominator, x here, and sine x here going to give you 0 on the numerator as well. So everything going to be 0 over 0. Well, now you can apply the L'Hopital rule. So let's do the L'Hopital rule. For the first time, so I'm going to differentiate. Well, the top one, so I differentiate x cosine x. So what happened is I get x negative sine x and then plus cosine x. This is by the product rule. and then I differentiate. Hopefully you can follow me. I differentiate that, I get that. And then I differentiate negative sine x. So I get negative cosine x, right? And then on the denominator, I have x cosine x, right? Because x and differentiate sine, get cosine, and then plus sine x. Well, this is x sine x, I differentiate, I get that. Well, now it's time to simplify it, because you can see that what is good here is the term that I have here, cosine x, gonna cancel with negative cosine x here, cancel out. So I actually have negative x sine x on the top, and I only have x cosine x plus sine x in the bottom. Well, it is still indeterminate from 0 over 0, but you know, we're gonna differentiate one more time, because we hope that something gonna cancel again. All right, differentiate one more time. Negative, well, differentiate x sine x, you get x cosine x plus sine x. All right, good. And then over differentiate x cosine x, you get x could multiply cosine, this is negative sine. All right, and then plus cosine x, and then differentiate sine, you get cosine. Is it better? So you can see that on the top, if I plug in x equal to 0 here, so you're gonna get negative. Well, negative, you plug in that, you get 0 plus 0. So on the top, you still get 0. But on the bottom, this is something better, because you have cosine here and cosine here. Cosine 0 is 1. So you have 0 plus 1 plus 1. Wow, actually this is 0 by using the L'Hopital rule. So this is 0 over 2, which is actually 0. Well, after you use the L'Hopital rule, it is better, because it clear out the denominator. So the denominator is no longer 0. So you have that thing. This is how to fix the indeterminate form infinity minus infinity. Does it make sense? Well, you can ask me, what if I cannot simplify infinity minus infinity? Well, that will not be asked for this class, because for this class, we're gonna ask you, if we ask you for the problem infinity minus infinity, it's gonna be the one that you can simplify. It usually starting from trigonometric function, because you can change cotangent to cos over sine, you can change tangent to sine over cos or something. So usually when we ask you to solve the problem about infinity minus infinity, it's gonna come with the form of trigonometric function, because you can simplify that. Well, you have no other ways to do indeterminate form infinity minus infinity at this point. We want you to simplify if you want to do it. All right, this is 4 p.m. now. Any questions? All right, I'm sorry that today we just need to be, the content is so heavy for today, because, well, we don't have time left. You just need to submit the homework this Saturday, so we have to complete chapter 5. So another 20 minutes, the last 20 minutes, we're gonna look at the last technique for this chapter. All right, the last technique for this chapter is indeterminate powers. So we already learned that the 0 over 0 and infinity over infinity, this can be solved by using the L'Hopital rule. And then 0 times infinity, this can be solved by simplify back to 0 over 0 or infinity over infinity. The same thing, infinity minus infinity, this is the form that we ask you to convert it back to 0 over 0 or infinity over infinity, so you can use the L'Hopital rule. There are three other forms, which is 0 to the 0, infinity to the 0, and 1 to the infinity. They are all indeterminate form as well. Well, these are indeterminate form that you can solve by take log. So if you see this type of indeterminate form, the idea is take log. Once you take log, you're going to use the property that you can swap the limit sign. Swap the limit sign and log. And then once you swap limit sign and log, you compute limit first, and then your answer going to be e to the something. Does it make sense? So this is the same technique that we learned in chapter 4. So if you want to read this thing, you can read it by yourself, but we're going to show you by examples because, you know, we don't have time now, only 20 minutes left. So we're going to just do examples. So hopefully you learn from example, but the idea here is you take log first, and then you swap limit sign and log sign. And then you know what, if you see example, you're going to say, hey, click. This is what we just learned in chapter 4, and we repeat it. So the idea is if you have 0 over 0, if you take log, it's going to come to 0 times log 0, which is 0 times infinity. If you have infinity to the 0, if you take log, it's going to come to 0 times log infinity, which is 0 times infinity. Well, if you have 1 to the infinity, if you take log, this is going to be infinity times log 1, which is infinity times 0 as well. Well, any form of indeterminate power, when you take log, it's going to come back to 0 times infinity, which is going to give you back the L'Hopital rule at the end. All right, I think I talked too much. So we're going to look at examples now. All right, let's start by, from the simple one. I want to evaluate limit of tan x to the x. All right, for sure, this is indeterminate form. Well, of the form, if you plug in 0 here, you get tan 0, which is 0 to the 0. Well, 0 power 0, this is undefined mathematics. So you don't know how to compute this thing anyway. So we need to take log. So we're going to take log of limit tan x to the x. Well, trust me that every time you see the problem like this, take log first, everything going to be a lot easier. Once you take log, you can swap limit sign and log sign. All right, the step is take log and then swap limit sign and log sign. And then after that, you're going to use the property of logarithm, move x down here. The reason why we take log because we want to move the power down. So we're going to get x log tan x. Here we go. This is come back to indeterminate form 0 times infinity, right? Because log of 0 is infinity. All right, and then now I need to just simplify more. So I'm gonna keep log tan x on the top, and then I'm gonna move 1 over x down. Well, so this come back to indeterminate form infinity over infinity. Perfect. Now we're gonna apply the L'Hopital rule. So it's gonna be limit x go to 0 plus here. Well, differentiate log tan, so I get 1 over tan. And then differentiate tan, I get secant square. This is by the chain rule. And then here differentiate 1 over x, you get negative 1 over x squared. All right, that looks good to me. Now we just simplify a little bit more. So I move negative x squared to the top. All right, over tan x. Well, how could we solve this thing? So if I plug in x, this is still 0. If I plug in 0, this is still 0, right? Tan 0 is 0. So this is still indeterminate form 0 over 0. Well, we need to apply the L'Hopital rule one more time. So we're going to get limit. Well, let's apply the L'Hopital rule one more time. So, oh, 1 second. before we differentiate, I think we can cancel something because tan and secant, you can cancel, right? So what I'm gonna do is, let's see, tan and secant. So I can say, well, I'm gonna change it to sine and cosine, so it's a lot easier to differentiate. 1 second, I think. Just, well, I do not want to differentiate x squared times secant squared because it's going to be messy. So I'm going to just swap tan to sine over cosine. And then that secant is 1 over cosine, right? All right. That's look better to me because I can cancel cosine now. Negative x squared over sine x cosine x. All right, good. And also, if you use a technique that we learned, well, you do not need to do the L'Hopital rule. Actually, if you move x down one time, so you're going to have sine x over x. And then you have cosine x here. So I move 1x down to the bottom because I want to keep sine x over x here because I know that sine x over x is going to be 1. Right? Limit of this thing going to go to 1 from the knowledge from the before midterm. So actually, I only have limit x go to 0 plus negative x over cosine x. Wow, this is 0 over 1. This is 0. Well, if you do not want to use the limit sine x over x, you can differentiate as well. But I'm trying to avoid, avoid the messy thing because, you know, differentiate x squared times secant square x could be a pain. You see that log of this thing highlight in orange, it's just 0. Well, this means just the thing that I highlight in orange. This is going to be e to the 0, right? Because, well, think again, log of that orange thing equal to 0. That means the orange thing is e to the 0, which is 1. Well, this is your final answer. Does it make sense? This is how we do the indeterminate form, the power thing. So, well, again, I will repeat this thing and then I'll answer a question in the chat. Well, the idea is you take log first.
Why is it 1? Why is the final answer 1 and not 0?
Here, you have log of limit tan x to the x, where x go to 0 plus. This is 0. Well, but the thing that you want to find is the thing that I highlight in orange, right? Log of the orange thing equal to 0, which means just the orange thing here. This is going to be e to the 0, which is 1. Does it make sense? Well, this is how we answer. You have to convert back into thing that you know. Well, you take log first because you want to simplify it easily. And then after that, you have to go back to e to the something. Well, we don't have much time left, but well, I'm gonna show more example in the clip. But before that, let's go back one slide because Sirapop asked me to go back last slide here. So this is the theory that we are going to, once you see 0 to the 0, infinity to the 0, 1 to the infinity, well, we can take log. So it's go back to 0 times infinity. And then you compute limit first. Once you compute limit, now you can you compute limit first, and then now we get the answer. Suppose this is L, then you can answer e to the L is your final answer. So we have one more question from Shuin. He asked us that why can't we simplify 1 to the infinity to 1? Well, this is not actually 1 to the infinity. The notation 1 to the infinity here, this is something that is limit go to 1, raised to limit go to infinity. This is not 1. The base here, this is not 1, but this is the notation stand for the limit of the base thing here approach 1. So it doesn't mean that this is 1. Well, does it make sense? So this is not 1. This is something close to 1, less to something close to infinity. All right. Log 0 equal to someone say on the chat, log 0, is it equal to infinity or negative infinity? Yeah, Pawin, log 0 is negative infinity, right? Because, well, you see that log infinity here, here. Log x, where x go to 0 plus is negative infinity, which means log of 0, this is negative infinity. So let's say you have limit of this thing. So if you plug in 0 here, you're going to see you have e to the 5 times 0 plus 0, 1 over 0 here. This is 1 to the infinity. So you can see that the base here gonna be the thing that goes to 1 where x go to 0. This is the thing that goes to infinity where x go to 0. It is not actually 1. Well, if you plug in, yeah, you get 1, but this is not actually 1. This is something close to 1 because x go to 0. X is not actually 0, it's just go to 0. So this is actually indeterminate form, 1 to infinity. Well, again, when you do this, so you take log first. Well, maybe I'm sorry that today I used 90 minutes for the class. All right, so after we take log, we're gonna swap limit a log side. Well, I'll do it quick. Log side here, right? Well, I swap limit a log. I'm sorry that the parenthesis is not right. It must be that chip, right? And then I swap log and limit. Okay, I swap log and limit. I didn't do anything. I swap log and limit. Good. And then after that, I take 1 over x down. And then after that, once you take 1 over x down, it's going to come back to indeterminate from 0 to infinity for sure. Well, to make it easier, so I'm going to do limit x go to 0 log e to the 5x plus x over x. Here on the numerator, this is something goes to 0, right? Because you're going to get log 1, which is 0. Here you're going to get 0 as well. So you have indeterminate form 0 over 0. Now, hey, L'Hopital, help me, L'Hopital. Well, L'Hopital, stay with me. And then that, I differentiate that. Well, it's going to be the one that we need to differentiate log. So differentiate log u, I get 1 over e to the 5x plus x. Well, we differentiate e to the 5x plus x inner function. I have 5 e to the 5x plus 1. Differentiate x, you get 1. All right, let's simplify a little bit so it's a lot cleaner. So I have 5 e to the 5x plus 1 over e to the 5x plus x. Is that better? So you can plug in the number 0 now to see if it's still indeterminate form. So 5e to the 0 plus 1 over e to the 0 plus 0, right? That is 6 over 1, which is 6. Hey, we got the answer. However, some of you are going to answer 6 and you're going to lose your point because the real answer is to sum up the limit of e to the 5x plus x to the 1 over x here, this is going to be e to the 6. Because log of that, the one that I highlight in yellow, log of this is equal to 6. That means just this thing, e to the 6 is your answer. Well, after 2 examples, I think you saw the technique, right?